now we are going to talk about the entropy change due to heat and work, and before that I would like to remind you our discussions about microscopic understanding of heat and work. So, by now you know that that any system can be described as particles occupying different energy levels. So, be it harmonic oscillator, particle in a box are good examples of that. Even for realistic system, one can solve quantum mechanical problems and can get different energy levels, however close they are. We know that for a very high temperature systems the levels are very close together, and therefore, it behaves classically, but again it is always we can have different levels always if we want to. So, microscopically if you look at it, the internal energy of a system is obtained from how the particles are distributed in different levels. For example, this system the internal energy is 1, and why so? Because again the 4 out of 4 particles 3 are occupying the 0 energy level and 1 is occupying the first energy level. Now, when you put heat to the system, and you know the heat from the first law, heat, internal energy and work, they are all equivalent thing, right. So, when you put heat to the system, now then what will happen is that the energy of the system now goes from 1 to 2. Now, how can it go to 2? Either one more particle, okay. So, we are using 2 units of heat here actually. So, you know how it can have once then it will have 3 units of heat, right, from 1 to 3. Now, how it can have 3? Either either I can take this particle to the second level and one more particle from 0 to this level. I can do that, or I can do in many different ways. I can put all the 3 particle to the first level and 1 particle in 0th level, and many different ways we can do that. But the main point here is to show you is that whenever you put heat to the system, the particles get distributed to other levels, and that is how the system will absorb the heat. However, when you do work, does it happen that way? So, when you do work on the system, we know that not the heat, just the work on the system, we know what happens is that the volume decreases, right. So, what happens if the volume decreases? Now, from a particle in a box example, I would like to remind you is that you know that energy of a particle in a box is n square h square by 8 m L square, and L is the length of the box. So, wherever L decreases, wherever length decreases, energy will increase because they are inversely proportional. So, what happens when you do work on the system, your length of the box decreases and your energy levels which were separated by let us say 1 unit will increase by larger unit. Here we are using a very simple example and showing that whenever you do let us say 1 unit of work, W equal to 1, then what happens is that the energy spacing itself increases to the double, but you notice that particle remains distribution remains same. That means 3 particles still is in the ground state and 1 particle is in the next excited state. However, the energy of the next excited state itself is now equal to 2 instead of it was equal to 1. So, the gap itself increases, particle distribution did not change, just the gap itself changes. So, whenever you put heat, then particle distribution changes, but when you do work, then the work itself changes the energy level of the system. Energy levels will change, and if energy levels change, you know the overall energy of the system will change, and that example that you can understand from particle in a box itself. Very good question. So, the question is that then will work change the entropy? We are going to discuss that in a moment. Why heat flows into the system? So, why whenever we try to heat a system, it actually goes into the system? Of course, not a hot system. Of course, you cannot heat a system by a colder system, but always if we bring in a hotter system, the heat will flow into. So, why heat flows into spontaneously into a system, and that is what we are going to see, because when something drops, the kinetic energy gets dissipated to heat and then it goes to the floor and all. So, it is easy for the heat to flow in. Why is the case that you are going to see? Let us take a system, and these examples we have done before. So, you are already familiar with that. So, let us start with a system of 0 energy. So, U equal to 0 and number of microstates, capital W is number of microstates, is 1 right now, because there is only one possible ways of doing so, because they are all in the 0 level. Now, let us put some heat to the system, and you know what happens when you put heat to the system? The particle changes, energy levels remain same, particle distribution changes. So, put Q equal to 1. So, energy now will become 1. and one particle has to go to the next level. Now, how many ways we can do that? I can put any of the 3 particles. So, W becomes 3. So, as you can see, when you try to heat a system, it will go into the system because W increases, because W increases means entropy increases, and entropy increase is a favorable process. We know that, because there is just only there are only possible things to happen. Now, put one more heat to the system. Now, what is going to happen? Now, our total energy of the system now is 2. Now, I can do it in 2 possible ways. I can either take one particle to the second level, and that is 3 possible ways of doing so, because I can take any 3 of the particle, or I can take 2 particles to the higher level, and that is also there are 3 possible ways of doing so, because I can take 2 of the 3 particles, 3C2, which is 3. So, total number of possibilities I get is 6 when we are heating the system. So, you see, as and when we are heating the system and as and when the internal energy of the system increases, number of microstates increases. So, in a way you can say that entropy is proportional to microstate. Okay, I will just go one more example and come back to that. Now, put one more heat to the system. Now, what happens is that now our energy of the system is 3, and now there are 3 possible ways of doing so, 3 possible distributions of doing so. We already know about that. Either we take all the 3 particles to the first level, and that is only one way of doing so, or we can take one particle in 0, one particle in 1 and one particle in 2, and there are, as you know, 6 possible way of doing so, because I can take 3 possible ways for the second one and 2 possible ways of this one. So, there are 6 possible ways, and I take one particle to the third level, and that is 3 possible ways. When I add them up, there are 10 possible ways of putting the heat. So, you can see that W is proportional to energy, and therefore, S is also proportional to energy. So, with the amount of energy, entropy also increases. So, entropy is actually proportional to energy, and that is one of the postulates of thermodynamics when it is taught in a postulate based way, that entropy is a monotonically increasing function of energy. And you will see soon enough, or I can already discuss to you, because we have already discussed about that, is that we know from classical thermodynamics that dq reversible by T is nothing but ds, or dq reversible is actually Tds, right. And then we know that whenever we say that, let us say work done is 0, then it will be nothing but dE, and then as you can see that dE by ds at a constant volume, whenever there is no work, it is nothing but temperature. So, because temperature can never be negative, you can see that whenever the entropy will increase, our energy also have to increase at a constant volume, though, if there is no work done, that is the constraint that we have to put into the system. So, without doing the work, here we are not doing the work because there is no change in the energy levels taking place, that is why there is no work done here, but there is only heat is going in, which means the internal energy of the system is increasing, and that is increasing the number of microstates, and that has to happen because that is what temperature is, and temperature cannot be negative. And that is one interesting thing to really think about. And this is I will just clear out the pen marking, and you can see exactly the same thing I have written here that we have discussed already. So, now let us see how work affects the entropy. Now, let us say we take the same system where there are 3 particles and one particle is in the level 1, and this 0, 1, 0 they denote just the energy of those particles. For example, these 2 particles are in the 0 level, that is why I mentioned at 0, and one particle is in the higher level, that is why it is mentioned at 1. So, this configuration is where the left particle has a energy 1 and other 2 particles 0, and this configuration is where the last particle is 1. So, these 3 configurations are denoted by that 0, 1, 0. Now, let us say I do 1 unit of work on the system, and you know what is expected is that the spacing itself now changes. It absorbs the energy, but just the way that the spacing energy spacing changes without changing any distribution of the particles. And we see that the number of microstates is not going to change anymore, because they are just going to remain same. Even though the energy gap is higher, that does not matter. So, does it mean that when you do work on the system, the entropy does not change? But then that immediately gives us another question, that what happens for an expansion process? because an expansion process, it gives more number of microstates. We know that anywhere whenever there is, we talked about an expansion, there is more accessible states for the system, and therefore more entropy should have come. But we have seen in the Carnot cycle that in the adiabatic expansion or compression process, there is no change in entropy, because dq reversible by T is 0. We see that from the first law of thermodynamics also, that du equal to dq plus dw, and when it is done in a reversible manner, then the entropy change is nothing but dq reversible by T and nothing to do with dw. So, if dq reversible is 0, then entropy is 0, and that is what happens for adiabatic expansion and compression process. Now, in expansion process, entropy should have increased due to larger accessible microstates. However, at the same time, the temperature of the system is decreasing, and because of the temperature of the system is decreasing, it does not have really energy to access the accessible states. So, therefore, the entropy cannot increase in that case, and same thing happens for the compression process. In the compression process, the volume decreases, but it should have therefore, since decrease the entropy, but it has now increased temperature, which means that it can now access more number of states, and therefore, it will compensate that. So, this adiabatic expansion and compression processes, these two opposing phenomena of expansion and not having enough energy to access, is actually compensating each other, giving rise to the fact that during the work done, you do not get to see any change in the entropy. Now, let us talk about heat flows from hot to cold. So, you remember this heat flows from hot to cold spontaneously is from Clausius's theorem of second law of thermodynamics, that heat will spontaneously go from high temperature to low temperature or hot to cold, and not the other way around spontaneously, and that was the basis of classical thermodynamics explanation. And there was no microscopic basis to understand that at that point. It is just a phenomena, just an observation. It never happens the other way. Something always will fall down from up to down. It will not go other way. The particle will not fly away or levitate, right. So, this is an observation from which we they have built the thermodynamics, classical thermodynamics subject. Whereas, from Boltzmann point of view, from atoms and molecules and number of microstates, a parallel process is going on, a parallel way of understanding is going on. However, they are connected. We will make those connections between classical and the statistical laws, but right now we are only talking about number of possibilities, number of microstates. So, here we see that how the number of microstates can help us understand that heat will always go from high temperature to low temperature. So, let us take a system where the internal energy of the system is 4, and we have taken a very simple 2-level system with 10 particle. So, now 2-level system 10 particle, meaning that 4 out of the 10 particle will have to go to the higher level, okay. And that is the reason that it will have the 4. Now, how many possible ways you can do that, because all are distinguishable particles. So, I have to choose 4 out of the 10 in order to put them to the higher level. So, I do 10C 4 ways, and you know 10C 4 is how much. So, let us calculate that and show you. 10C 4 is 210, and we wrote as 210 here already. Let us take another system where the energy is only 2, and again I have to choose 2 out of 10 particle in order to put them to the higher level, and that will give us 10C 2 number of possibilities, and that is 45. So, WA is 45 and this should be WB. WA is 45 and WB is 210. So, when you make them together, say the system together will have how many microstates? It will be product. Remember, never add them, because as you know, entropy is additive quantity, just like volume. Just like volume of A and volume of V combined together will be volume A plus volume B. Similarly, entropy of A and entropy of B will be added together as entropy of A plus entropy of B. However, whenever talking about microstates or number of possibilities, the number of possibilities of A and number of possibilities of B is always a product. So, therefore, when you do that, when you do that, what happens is that W A is 45 and W B is okay, W A is 45 and therefore, entropy of A is KBln W A, which is KBln 45. Okay. Now, W B is 210. So, entropy of B is KBln W B, which is KBln 210. When you add them together, what is happening is we are adding entropy of A and entropy of B. We are adding entropy of A and entropy of B, and you see what we are doing, we are multiplying them. We are multiplying the microstates and that becomes KBln 9450. That is very important point whenever you are talking about two different systems, and that is the reason I told you, right, that entropy is proportional to W, number of microstates, but this proportionality comes with an ln function, a function of W I should say. Now, comes with a logarithm function. The main reason is that while microstates are multiplicative, entropy is additive, and that is only possible if you put an ln function in between, and that is why that ln come in between, because so that we can actually add the entropy and multiply the number of microstates. That is very important point. Now, let us transfer heat from high temperature to low temperature only. So, I take this one of the particle and put it here in this level. So, now the energy of this system will become 3 and energy of this system also will become 3 now. Earlier it was 4, you see, earlier it was 4 and it was 2. Now, we are taking it 3 to 3. Okay. Let us see what will be the repercussions for that. So, now UA is 3 and how many ways we can do that? 10C 3 ways. So, when you do 10C 3 ways, the earlier if you remember earlier how much it was 45. So, I have put one more particle, like you can see here, this particle I have put up on the first level. Earlier only 2 particles were there, now there are 3 particles. So, now it has become 45 10C3. Is it 45? Let me do 10 into 9 into 8 by 3 into 2 into 1. So, 3 3s are 9 and 2 4s are 8. So, 120 ways. Earlier it was 45 alone, but at the same time, so that means the entropy of this A system has increased, because earlier it was 45, now it is 200 and now it is 120. So, entropy has definitely increased for the left system. However, at the same time you remember that earlier it was, this should be B and this also should be B. Earlier it was WB was 210 and now it has become 120. So, it has reduced now. So, it is whenever there is a heat transfer, do not think that both of them are gaining entropy. One is losing and another is gaining, but together they are gaining. That is the point that we are going to show. So, it has lost entropy by giving away heat, it has gained entropy by taking in heat, and when you combine them together, what we see, number of microstates now for, so again, so W A is 120, entropy is KBln 120, W B is 120 because the same, and KBln W is 120. Together is how much? W A into W B. So, 120 into 120 giving rise to 14,400. Do you remember how much it was before? How much the combined system entropy earlier was? KBln 45 multiplied by 210, which was KBln 9450. So, from 9450 it has increased to 14,400. So, you see, although one part got lesser entropy, another part got more entropy, in a combined manner they got more entropy, and that is the reason the heat will flow from high temperature to low temperature. Now, you should do one calculation, instead of like earlier it was 4-2 distribution of energy, right, you should transfer heat from low to high. That means, you make it 1-5 and see whether the number of microstates for the combined system increases or not, and that will tell you that whether it will be possible or not. So, now you see that why spontaneously heat will transfer from low to high, high to low. The reason is that it is just more probable, because it will just give more number of microstates, more possibilities, and that is why heat will always flow. So, microscopic molecular thermodynamics gives a microscopic understanding why heat flows. Classically, it is just a postulate. Statistically, it is not a postulate, it can be shown, whereas statistically the postulate lies somewhere else. It says that that entropy is proportional to number of microstates. That is a postulate for statistical thermodynamics or molecular thermodynamics, whereas this can be derivable. In classical thermodynamics, the postulate starts with the fact that heat cannot transfer from low temperature to high temperature. Yeah. So, the question is that whatever amount of energy that is being transferred by the hot object, it is received by the cold object. So, dq is same in both the cases. In one case, why the entropy, then why together entropy is increasing? Because we have to remember always the fact that there is in the denominator the temperature, that is an integrating factor. So, you are transferring heat from a high temperature, which is already having a more accessible state, to giving it to a low temperature object, which is not having that many accessible states, and somehow though the quality of heat becomes better when it is given to a cold object. By quality I mean the number of possibilities that can be. So, a rich person is already rich, it does not have much avenues to, let us say, spend it, but then if you give it to somebody who does not have that, probably you have more avenues to spend it.